All right, welcome. Today we're going to tackle a huge problem, one that can bring even the most massive systems to a grinding halt. And we're going to solve it with one of the most elegant, memory-saving patterns I know. Okay, let's get into it.
Okay, picture this. It's the championship final. Your sports betting platform is live and you've got this many users. 50 million, all hitting your servers at the exact same time. And these aren't just simple logins, right? Every single one of them is pulling down rich data about the teams. We're talking rosters, high-res logos, historical stats. These are heavy objects, packed with info.
So if you just do the obvious thing, create a new data object for every single one of those user requests, this is how much memory you'd need. 250 terabytes. Just let that number sink in for a second. It's insane. And look, this isn't just some textbook problem. Your system is literally seconds away from a catastrophic out-of-memory error. Your service is about to go completely dark during the most important moment of the year. So, what do you do? So, here's how we're going to break it down. First, we'll dig into that 250 terabyte problem. Then, we'll unveil the solution, the Flyweight Pattern. We'll look at how to build it in Go, clear up some common confusion, and finally talk about making it truly production-ready. All right, first up, let's really nail down what this problem is all about. It's this fundamental tension, right? You need to serve up this rich, detailed data for a great user experience. But when you try to do that at a massive scale, the memory cost just explodes. This quote from the source material just hits the nail on the head. The choice you make here isn't about a little performance tweak. No, it's about survival. A simple decision in your code literally determines whether your entire application lives or dies under load. And you know what? This problem is everywhere, not just in sports betting. Just think about a game like Minecraft. It's not like it stores a whole new data object for every single grass block in the world. That would be impossible. Instead, it creates one grass block, Flyweight, and then just points to it millions of times. It's the same idea for fonts in your text editor or CSS styles in your web browser. This problem is hiding in plain sight. Okay, so how do we fix this 250 terabyte nightmare? We use the Flyweight pattern. It's a design pattern built specifically for this exact scenario, efficiently managing a huge number of objects that all share a lot of the same data. Okay, this slide is everything. Just look at the difference. On the left, you've got our disaster scenario. But on the right, that's the Flyweight solution. So instead of creating a unique 5 megabyte object for all 50 million users, we create just two heavy objects, one for Team A and one for Team B. And then everyone else just gets a tiny little 8-byte pointer to one of those two objects. The result? We go from 250 terabytes down to about 410 megabytes. I mean, that's not an optimization. That's a different reality. It's a total game changer. So what's the magic trick here? How does it work? Well, it all comes down to one simple but brilliant idea. You split the data in your object into two different parts. And this separation, this is the whole secret sauce. You have your intrinsic state. This is the heavy, shared stuff that's the same for everyone, like the team name and its logo. This lives inside the Flyweight object. And then you have the extrinsic state. This is the stuff that's unique to each user, like their user ID or how much they bet. This stuff lives outside the Flyweight and just gets passed in when you need it. If you can wrap your head around this one concept, you've basically mastered the entire pattern. All right, so let's get our hands dirty and see what this looks like in actual code. To make the Flyweight pattern work, we need a gatekeeper, something that makes sure we never accidentally create a duplicate object. And that gatekeeper is called the factory. And the logic here is actually super simple, which is what I love about it. When a request for, say, Team A comes into the factory, it just checks its internal map. It basically asks itself, hey, have I seen Team A before? If the answer is yes, it just hands back the pointer it already has. If the answer is no, then, and only then, does it create the new heavy object, stick the pointer in the mat for next time, and then return it. Simple as that. Oh, and a quick little aside here. In the Go code for this, you'll probably see the iota keyword. It's just a really clean, Go-specific way to create a sequence of numbers, like team IDs, without having to type 0, 1, 2, 3 yourself. Just a cool little piece of Go elegance for you. Okay, this right here, this is the moment of truth. How do you actually prove that it's working? Well, you ask the factory for Team A, and then you ask it for Team A again. The question is,
Did you get two identical but separate objects, or did you get two pointers pointing to the exact same object in memory? In Go, this simple check, team A1 equals team A2, doesn't compare the data inside. It compares the memory address. That's the test. That's the invariant. If that line is true, you're golden. Okay, let's talk about something that trips a lot of people up. They hear one instance and they immediately think of another pattern, the singleton. They both control how objects get created, but they solve totally different problems. Let's clear this up right now. So a singleton is super strict. You get one instance of a thing. That's it, the end. But a flyweight is different. You get one instance per unique state. So in our betting app example, the factory that creates the teams, that's a singleton. You only want one factory. But the team objects inside its map, those are the flyweights. You have one for team A, one for team B, etc. So they're not enemies. In fact, they're often best friends. All right, so we get the theory, we've seen the basic code, but what about the real world? What happens when you have thousands of concurrent requests all slamming that factory at the exact same millisecond? And this is so important because it's what separates classroom code from production-ready code. A standard map in Go is not safe to be read from and written to by multiple threads at the same time. You'll get what's called a data race. To fix this, you have to protect the map with a mutex. A sync.RWMutex is perfect here because it lets tons of users read from the wrap at the same time, but puts up a gate when that one rare request comes in that needs to write a new team to the map. Now, before you run off and build this whole thing from scratch, you should know that Go actually has a built-in tool that's kind of like a flyweight called sync.Pool. It's specifically designed for reusing temporary objects that are expensive to make, like buffers for handling individual web requests. For that kind of job, it's the go-to tool. Okay, so let's do a quick lightning round of the key takeaways here. 1. Always test your invariant. Same state must equal the same pointer. 2. You have to get that separation between intrinsic and extrinsic state right. 3. Remember, the factory is a singleton that holds all your flyweights. 4. Any shared data has to be either totally immutable or protected by a mutex. And 5. Before you build your own, always check if sync.Pool can do the job for you. You know, when you really think about it, this pattern changes how you look at system design. In a world with massive scale and limited resources, we're so often focused on CPU speed. But sometimes, the better question isn't how fast can it go, but how light can it be? So I want to leave you with a question to take back to your own work. Your memory is finite, but pointers are incredibly cheap. So where, in your system right now, is there a heavy object you keep creating over and over again that's just waiting to become a flyweight?